Dear students, in the last class, we have discussed about the crystal field theory, and we have also discussed the various points regarding the crystal field theory. This theory says there are 5 d orbitals. Out of the 5, 3 d orbitals, namely dxy, dyz and dxz orbitals are in between the axes, and dx square minus y square and dz square orbitals are along the axis. Because of this, there is a slight energy difference between these two orbitals, and when the ligand approaches to the metal ion, there is a splitting of these d orbitals takes place, and the orbitals which are in between the axes are called T2G orbitals, and the orbitals which are along the axis, that is dx square minus y square and dz square orbitals, are called EG orbitals. And there is a difference in energy between the two. That energy we call it as delta or 10 dq. It is also called crystal field stabilization energy. We have studied what is crystal field stabilization energy and their calculations, and also the pairing energy. We have also discussed about the crystal field splitting in octahedral complexes. In this complex, there are two types, that is called the high spin complexes and low spin complexes. So, in the last class, we have studied about the calculation of crystal field stabilization energy in case of low spin complexes. In this case, the energy difference between T2G and EG orbitals is very high. Because of this high energy difference, the fourth electron, it gets paired up in the T2G itself rather than going into the EG orbitals. And the calculation of CFSC, which is shown in this table, is already discussed in the earlier class. Let us today we calculate the calculation of crystal field stabilization energy for high spin or weak field complexes. In this complexes, the crystal field stabilization energy, the 10 dq, is very small. So as a result, the fourth electron goes into the T2G orbitals rather than fourth electron goes into the EG orbitals rather than in T2G orbitals. Now let us see how to calculate the crystal field stabilization energy in these complexes. Both in low spin and high spin complexes, D1, D2 and D3 systems have -4, -8 and -12 dq respectively. But in D4 system, the number of unpaired electrons here will be 4 and electronic configuration becomes T2G3 EG1. So when the electron goes into the EG, the CFSC becomes -12 plus 6 is equal to -6 dq. Similarly, for the D5 system, 5 unpaired electrons, the spin will be 5 into 1 by 2 will be 5 by 2, and the distribution of electrons will be T2G3 EG2. The CFSC is -12 plus 12 is equal to 0 dq. Similarly, for D6, D7, D8 and so on, the CFSC will be -4 dq plus 1 pairing energy, -8 dq plus 2 pairing energy, -12 dq plus 3 pairing energy, and so on. And in this case, the 10 dq value is less than the pairing energy. Now let us study the crystal field splitting in tetrahedral complexes. today. In tetrahedral complex, the coordination number is 4. It is seen from the figure that the 4 ligands placed at the corners of the tetrahedron are located at the 4 corners of the cube, which are lying in between the 3 axes, that is X, Y and Z. In case of tetrahedral complexes, as the ligand approach the central metal ion in between the axes, the energy of T2 orbitals increases much more than the energy of E orbitals. This is because the approach of ligands and T2G orbitals are in between the axes, which results in increase of energy. Here, we call T2 and E orbitals. There is no G. The G is referred to the G-rad, which is applicable for the complexes having center of gravity. Tetrahedron is not having center of gravity. The word G is not used. This is the slide. It shows the splitting of the orbitals in a tetrahedral field. As it is said, in tetrahedral field, the ligands approach in between the axes. Since the dxy, dyz and dxz orbitals are in between the axes, they get higher energy, and the dx square minus y square and dz square orbitals, they lie along the axis, they get lower energy. Crystal field splitting in tetrahedral complex is illustrated. In the first stage, the degeneracy of all the 5 orbitals in the isolated central ion. In the second stage, hypothetical degeneracy of all the orbitals at higher energy level. Third stage, the crystal field splitting, as I have shown in my previous slide. Crystal field splitting by convention is taken as 10 dq or delta T. In tetrahedral complex, the energy of the E orbitals is 6 dq or minus 0.6 delta T, and the energy of T2 orbitals is 4 dq or plus 0.4 delta T with respect to hypothetical degeneracy of orbitals. As the tetrahedral complex involves 4 ligands and octahedral complex involves 6 ligands, the relationship between delta T and delta O for the same metal ion, ligand and same internuclear distance is delta T is equal to 0.45 into delta naught. This means crystal field splitting in a tetrahedral complex will be about half the magnitude of that in the octahedral complex. This slide shows the same. Since there are only 4 ligands in tetrahedral complex, so the ligand field is roughly 2 by 3 of octahedral field. That is delta T is equal to 4 by 9 delta naught, which comes to be 0.45. All tetrahedral complexes are high spin since CFSE is normally smaller than pairing energy. If a very strong field ligand is present, square planar geometry will be favored. Now, I have shown here what is the reason for delta T is equal to 4 by 9 delta naught. There are 4 ligands instead of 6 in the ligand field is 4 by 6 is equal to 2 by 3. In tetrahedral, the direction of the orbitals does coincide with the direction of the ligands. This reduces the crystal field splitting by roughly a further 2 by 3. Thus, delta T is equal to 2 by 3 into 2 by 3, that is equal to 4 by 9. So, the subscript G, that is a G-rate, is not used for the splitting of d orbitals in tetrahedral complexes because a tetrahedron has no center of symmetry. Center of symmetry is found in octahedral and square planar complexes. In such cases, the subscript G, that is a G-rate, is used. The CFSE for tetrahedral complexes can be calculated by the same procedure as for octahedral complexes. Since the energy difference, that is between T2 and E, is small, the CFSE is small. Therefore, pairing does not occur in E orbitals. Hence, tetrahedral complexes are always high spin complexes. This is a table that shows the calculation of crystal field stabilization energies for the tetrahedral complexes. For D1 system, unpaired electron is 1, the spin is half, distribution of electron is even, so CFSE is minus 6 dq. For D2 system, it is E2, CFSE is minus 12 dq. For D3 system, 3 unpaired electrons, spin is 3 by 2, electronic configuration becomes E2, T21. So here it is minus 12 plus 4 is equal to minus 8 dq. For D4 system, it is E2, T22. Hence it becomes minus 12 plus 8 will be minus 4 dq. For D5 system, number of unpaired electrons are 5. Spin is 5 into 1 by 2 will be 5 by 2. So then electronic configuration becomes E2, T23. So CFSE is minus 12 plus 12 becomes 0 dq. So for D6, D7, D8 and so on, the pairing of electrons takes place. So therefore, the calculation of CFSE will be minus 6 dq plus 1 pairing energy, minus 12 dq plus 2 pairing energy, minus 8 dq plus 3 pairing energy, and so on. In this case also, the 10 dq is less than pairing energy. Hence, all tetrahedral complexes are high spin complexes. Now coming to the crystal field splitting in tetragonal and in square planar complexes. We have the tetragonal and square planar complexes. The splitting of d orbitals in tetragonal and square planar complexes can be understood by gradually withdrawing two ligands lying along the z-axis from an octahedral complex. In case of octahedral complex, 4 ligands are in one plane, 2 ligands are above and below the plane along the z-axis. When we remove these 2 ligands, now the coordination number becomes, instead of 6, becomes 4. And when we withdraw that, then we get complete withdrawal gives rise to square planar complex, and partial withdrawal leads to the tetragonal complexes. As the ligands lying on the z-axis are moved away, the ligands in the xy plane tend to approach the central metal ion more closely. This causes an increase in the energy of dxy and dx square minus y square orbitals in a tetragonal complexes. Because in these we don't have any z axis. As the ligands lying on the z axis are moved away, the electrons in the dxz and yz and dz square orbitals experiences relatively smaller repulsions from the electrons of the ligands. This results decrease in the energy of the dxz, dyz and dz square orbitals in a tetrahedral complexes. In square planar complexes, the ligands lying along the z-axis are completely dropped out. This further raises the energy of dxy and dx square minus y square orbitals and reduces the energies of dxz and dyz orbitals. As there is no approach of the ligand along the z-axis, the dz square orbital attains least energy. The crystal field splitting in the case of square planar complex is the energy difference between dxy and dx square minus y square orbitals. Here I have shown the crystal field splitting in square planar complexes as well as in tetragonal complexes. So the EG orbitals, it further splits into the two, that is the dx square minus y square orbital is having higher energy and dz square orbital is having lower energy. And T2G orbitals, they further split into dxz and dyz orbitals have lower energy and dxy orbital is having higher energy. This is in case of tetragonal complexes. When it comes into the square planar complexes, dx square minus y square orbital is having still higher energy, little higher energy, and the dz square orbital gets energies lowered than the dxy orbital. The same thing I have also given in this slide also, how the splitting of the d orbitals takes place in square planar complexes. So this is a slide showing the crystal field splitting both in octahedral and tetrahedral complexes. In the left side, we have the octahedral, the complex splitting, the crystal field splitting. In the right side, we have tetrahedral splitting. This is a slide that shows all the three types of the crystal field splittings. In octahedral complex, the d orbitals, they split into T2G and EG. So the T2G is having lower energy and EG is having higher energy. In tetrahedral complex, as the orbitals are approaching in between the axes, therefore E orbitals, they have lower energy, that is a dx square minus y square and dz square, and T2 orbitals, that is a dxy, dyz and dxz orbitals, they have higher energy. In case of square planar complexes, it is similar to the octahedral, and in octahedral, the EG orbitals, they further split, wherein dx square minus y square orbital is having higher energy and then the dz square orbital, and further the T2G orbitals, there the dxz and dyz orbitals, they have lower energy and the dxy orbital is having higher energy. This further, in square planar complexes, the dz square orbital is having still lower energy than the dxy orbital. Therefore, the d orbitals with increasing energy is dxy, dyz, and then goes to the dz square, and then goes to the dxy, and then goes to the dx square minus y square orbital. Yes, this is a slide showing the strong and weak field ligands. So if the ligand is a weak field, when the ligand is a weak field, then the energy difference between T2G and EG is less. When T2G and EG is less, electrons goes to the singly T2G and EG orbitals, which results high spin complexes. In case of strong field, the energy difference between T2G and EG is high. So therefore, the pairing of unpaired electrons takes place in T2G first and then goes to the EG. This results low spin complexes. This is a table that shows the number of unpaired electrons both in octahedral having low spin and high spin complexes as well as tetrahedral complexes. If a complex is having a D1 system, so it contains one unpaired D1, D2 and D3, it contains 1, 2 and 3 unpaired electrons. When it comes into the octahedral D4 system, so for low spin complex it is 2, for high spin complex it is 4. In case of D5 system, for low spin complex it is 1, for high spin complex it is 5. Similarly, you go through the D6, D7 and further. The number of unpaired electrons in the system. In case of tetrahedral complex, we have only one type, that is the high spin type. That is, for D4 system, we have 4 unpaired electrons. For D5 system, we have 5 unpaired electrons. D6, we have 4, 3, 2, 1 and 0 respectively. This is called a spectrochemical series. We have a strong field ligands and we have a weak field ligands. So the strong field ligands, the examples are cyanide, carbon monoxide, the nitro group, ethylene diamine, ammonia. These are all the examples of strong field ligands. Water, oxalate, fluoride, chloride, bromide, these are all the examples of the weak field ligands. Now these ligands are arranged in the decreasing order of the ability to give the lone pairs of electrons. And this decreasing order is known as the spectrochemical series. In this, the cyanide is having a greater power and iodide is having the weaker power of donating a lone pairs of electrons. Now this crystal field strength, it depends upon the various factor. The crystal field strength or also the crystal field stabilization energy, it depends upon the various factors. Number one, the size of the crystal field splitting depends on the nature of the ligand. So if the ligand is a stronger ligand, so it leads to the low spin complexes. If the ligand is a weaker ligand, it leads to the high spin complexes. In case of octahedral complexes. Next, in case of tetrahedral complexes, if the ligand is strong field, it leads to the square planar geometry. If the ligand is weak field, it leads to the tetrahedral geometry. Coming to the another factor, that is the oxidation state of the metal ion. The crystal field stabilization energy is greater for tripositive ion than for dipositive ion. As the oxidation state increases, CFSE also increases. Third factor, the row of the metal in the periodic table. For a given ligand and oxidation state of the metal, the crystal field stabilization energy increases going down in a group. The crystal field stabilization energy for the metal ions of the first transition elements is less, but when we go to the second transition and third transition series elements, it goes on increases. The color of the metal complexes are due to electronic transition between the T2G and EG energy levels. Now, there are some factors also they affect the magnitude of the crystal field theory, which we have discussed. Here also the same thing I have given. This is also the crystal field splitting. They also depends upon the aspects what we have discussed just now. It also depends upon the principal quantum number. It also depends upon the repulsive ligand forces and so on. Dear students, go through the crystal field theory for the octahedral, tetrahedral, tetragonal and square planar complexes, how the splitting of the d orbitals takes place. Go through once again and try to understand the concept. Thank you.